Hi, welcome to Week 9, Part 1. We're going to do a quick review of some binomial facts, and that'll get us ready for the next thing to do. So this is another sort of thing that will be useful for the Homework 5 material. So a quick summary of the binomial distribution. I'll remind you that if x is a binomial n comma p distribution, then it has an expected value of n times p and a standard deviation of the square root of n times p times 1 minus p. So the expected value is a measure of center. So if x was, and I'll abbreviate here, binomial 100, 0.8, for example, then n is 100, and p is 0.8. So that means that the expected value, or the mean of x, is n times p, which is 100 times 0.8, or 80. The standard deviation of x is the square root. Remember, x is binomial. Oh, hello. Bit of a hiccup there. Let's try that again. So we're thinking of x as being binomial 100, 0.8. And we found that the expected value of x was 80. So the standard deviation of x will be the square root of n times p times 1 minus p, which is the square root of 100 times 0.8 times 0.2. which is the square root of 80 times 0.2, which is the square root of 16, or 4. Let me erase that. So to recap, if x is binomial 100, 0.8, the expected value of x is 80, and the standard deviation of x is 4. So this gives us a way of calculating a normal approximation for the binomial distribution. So again, the idea is we have two parameters, n and p. The expected value of the binomial distribution, the true distribution, is n times p. And the standard deviation is the square root of n times p times 1 minus p. Now, in order for this approximation to be reasonable, to be not too terribly far off, we're going to require that n times p, which we call the expected value, but you can think of it as the expected number of successes, has to be greater than or equal to 10. And if n times p is the expected number of successes, then n times 1 minus p would be the expected number of failures. And we also need those to be greater than or equal to 10. And as long as those two conditions are satisfied, then we're good to go. So let's look at an example. We have a large enough population. So 20% have green eyes. So x is going to denote a sample of people with green eyes. There's our 20%. And we're taking an SRS of size 100 And from that data, we're going to get a sample count x. So our question is, what is the probability that that sample has between 22 and 27 people with green eyes? And that's what we would like to be able to answer. So, how do we go about trying to answer that? Well, first off, notice that the sample count is effectively binomial. So as you may recall from the last video lecture, there are 5 conditions for a binomial distribution, right? So we have to have fixed number of trials n, success or failure on each trial. Number 2, we have to have constant probability of success. The trials have to be independent. We have to count the number of trials. So it's not quite binomial, because if I select one person, I have in a finite population, there's a slightly fewer number of people. But if the population is sufficiently large, that change is so minuscule that we can ignore it, and we do. So as long as, I forget off the top of my head, I think you want your population to be at least 20 times the size of your sample, something like that. So as long as that's satisfied, then we're just going to call it binomial. So remember, we had 20% of the people had green eyes, and we're counting the number of green eyes in 100. So the probability that x is less than or equal to is between 22 and 27 inclusive. Well, we have a bunch of mutually exclusive possibilities. So an event is the kind of thing that can happen. We're looking at a count. So if I get a count of 22, that's the total number of green eyes. I can't simultaneously have a count of 23. And if I have a count of 23, I can't have a count of 22, right? They're not the same count. I'm counting the total number of people with green eyes. So I have disjoint events, so I can calculate their probability by adding up the individual probabilities. So the probability that I get between 22 and 27 is the probability of getting exactly 22 plus the probability of getting exactly 23, and so on and so forth, adding up until we get to the probability of getting exactly 27. And as you may recall, the probability formula for a binomial distribution, for example, the probability that x is 22 is n choose k, p to the k, 1 minus p to the n minus k. And that's exactly what we're seeing here. N is 100, and we know that because it's right there. So there's our 100 there. P, 0.2. And we're seeing these 0.2s here as well. So we have our n is equal to 100s. We have our 0.2s. Now it's the k bit, right? So here, k is equal to 22. N choose k, p to the k. The probability of success is 0.2, then the probability of failure is 0.8. If we have 22 successes, then we have 78 failures, because those add up to 100, which is n. So again, the probability of getting exactly 22 successes is 100 choose 22 times 0.2 to the 22 times 0.8 to the 78. You should review the first, you should go through the chapter, the week 9 review, the earlier screencast for this. The probability of getting exactly 23 successes is 100 choose 23. That's 0.2 to the 23 and 0.8 to the 77. Keep adding those up. The probability of getting exactly 27 is 100 choose 27, 0.2 to the 27, 0.8 to the 73, because again, 27 and 73 add up to 100. Notice how all the little pieces fit together. always 0.2, 0.8, 0.2, 0.8, 0.2, 0.8, always 100, and so on and so forth. These guys match, these guys match, these guys match. 22 and 78 is 100. 23 and 77 is 100. 27, 73 is 100. So we calculate those things up, and again recall that n choose k, got ahead of the drawing, n choose k is n factorial divided by k factorial times n minus k factorial. So 100 choose 22 is 100 factorial divided by 22 factorial times 78 factorial. Not a coincidence that those numbers are the same as these. So this is 0.085 is the probability that x is 22. 0.72, rounded of course, is the probability that x is 23, that x is 24, that x is 25, that x is 26, and that x is 27. And you add them all up, and you'll get our answer, 31. So, out of all of the samples of size 100, about 31% of them should have a count of people with green eyes between 22 and 27. Now, if we want to do this in R, and we might want to, say for homework, we're dealing with a binomial distribution. So think of the D as being distribution and binom as being binomial. We give it the range of values, 22 up to 27. This is n. That is p. And I add all of those up. So if I do it in parts, D binom, 22 to 27, n is 100, p is 0.2. Here you'll see those numbers that I showed you earlier, but I'm not rounding them this time. So that expression is this collection of numbers in its entirety. Let me switch to a cooler color. And if I sum them up, then I'll get my 0.311852, a more exact example. Now, there's another way I can do this as well. There's another R command that's called p binom. So p binom gives me the lower tail area. So if I had my probability histogram, and I'll show you a nicer one here in just a second. You've got to imagine there's a bunch of numbers here. I'm going up to say, oh, let us undo that. Wow, that's impressive. Wait for it to catch back up to us again. So I have some histogram. I'll draw more slowly so I don't get ahead of this. And let's suppose this is 25, 26, 27. So the area of everything, all the bars up to 27. That's this. And then I'm subtracting everything up to 21. And notice 21 is not 22, right? I want the probability of getting a value between 22 Let me restart the drawing. Probability of landing between 22 and 27. And I apologize for how poor that looks. So here's a better picture. Here you can see the bars in red going from 22 to 27. I'm going to switch back to a red pen because that actually seems to be more efficient. 22 to 27. The area in red is my desired answer. Let's zoom in on that. So there you can get a better view of the 22 to 27. Now we also have this kind of lower tail area. So that's what that p-binomial is giving me. Everything up to 27. Oops, a little too far there. Okay, so now that we've got things straightened out, so we have (27), 26, 25, 24, 23, 22. That area in blue. So p-binomial 27, 100, 0.2 gives me the area of this rectangle and this rectangle and this one and this one, that one and that one and that one and that one and that one, and all of them all the way down to 0. But I only want the ones in blue, so I need to remove 21, 20, 19, 18, 17, and so on, all the way down to 0. And so the R command p-binomial 27, 100, 0.2 minus p-binomial 21, 100, 0.2 will give me that. And again, that's an exact answer. So I might want to ask myself, are the conditions apparently satisfied to use a normal approximation? So I need the expected number of counts. So that's to be greater than or equal to 10. So that's 100 times 0.2, that's 20. Yep, that's greater than or equal to 10. And then I need 100 times 0.8, the expected number of failures. That's 80. Again, that is greater than or equal to 10. So I'm good to go. So I do my calculation, and here we go. See, I use the normal distribution. So I had a mean of 20 and a standard deviation of 4, which we looked at earlier. And it totally works. Now, it's not the same thing as I got from p-binomial. This is an approximation. So 36.1%, 0.36 is not the 0.311 that we're looking for. And you can get a sense for that by looking at the two side by side. So on the left panel, here, doesn't like to draw too quickly. Sorry about that. I'm slow, it should work. Okay, on the left panel, you can see both the binomial distribution, which are the bars, and the normal approximation, which is that sort of red outline. And on the right panel, we have zoomed in. So the exact value that we want is the area in blue. That's the probability that x is 27, plus the probability it's 26, plus the probability being 25, and 24, and 23, and 22. The normal approximation, here's the 27. We've centered our bar, so the middle of the bar is on 27. We could have made a different choice, but that's the one that we did. So the area in red from 21 to 27, which you can see on the original, is the area that we actually get. And so you can see that's not quite the same. But it's an approximation. It shouldn't be. However, we could, if we were so inclined, modify things slightly, go out to 27.5, and start at 21.5. And that approach, which I'm not going to go into and I'm not going to require you to know, is called a continuity correction. I am just going to erase that. It's not fast enough for me to do that. So anyway, there's a continuity correction. So that's how you can use normal approximations to approximate binomial things. Again, the key thing that I want you to pay attention to is that when I wanted to estimate the probability of a binomial distribution being between 22 and 27, including 22 and 27, then what I used was a normal distribution, 27 down to 21. And again, if you look at these bars again, you'll see why that's the case. So, thank you very much for listening.